Hello, welcome back. Have you ever wondered how a compass works? Why do charges follow curved paths in a magnetic field? How electric motors spin? Or how we use the interaction between electric charges and magnetic fields to build devices like motors or accelerators? Let's talk about magnetism and the Lorentz force. A magnetic field is a vector field that exerts a force on electric charges that are moving. It can be visualized through magnetic field lines. We represent the magnetic field as a vector B. The SI unit for B is the Tesla, T. Who generates a magnetic field? Well, current carrying wires. Electric currents generate magnetic fields. The direction of the magnetic field is in loops around the straight wire. But we will talk about that in coming lessons. Magnetic dipoles, permanent magnets and current loops act as magnetic dipoles, generating field lines that emerge from the North Pole and enter into the South Pole. Permanent magnets microscopically are composed of lots of teeny tiny loops of current, electrons moving in circles, which are the ones generating a magnetic field of the magnet. The magnetic field of the Earth is created by the motion of charges in the core of the planet, which is made of metal at temperatures of around 6,000 degrees. In the end, all magnetic fields are created by electric currents. Magnetic field lines are represented by denser field lines for stronger magnetic fields, which they never cross, and they form closed loops. They go from the magnetic North Pole to the magnetic South Pole. Be careful, because the magnetic North Pole of the Earth is near the geographic South Pole of the Earth. So it is electric currents that generate magnetic fields. If you have a wire this direction and the current is going that way, let's say that my thumb is the direction of the current, the magnetic field curls this way in a direction of the wire. Now if you have a loop of current, then you have a loop like this, and the magnetic field is pointing this way. So if it's going counterclockwise, the magnetic field will be pointing up in the area of that loop of current. Let's talk about the Lorentz force for the magnetic fields. When a charged particle moves through a magnetic field, it experiences a force called the Lorentz force, which is given by F is equals to Q times V cross product B, where F is the force on the particle, Q is the charge of the particle, V is the velocity of the particle, and B is the magnetic field. Force is always perpendicular to both the velocity of the particle and the magnetic field. This is a direct consequence of the cross product, where it is a convenient way to determine the direction of the magnetic field is through the right-hand rule. So if fingers point in the direction of the velocity and the palm curves towards the magnetic field, then the thumb points in the direction of F for a positive charge. For a negative charge, it will be the opposite direction. It is important to notice that since F is always perpendicular to V, the force does no work on the particle. Therefore, the kinetic energy and speed of the particle remains constant, but its direction changes. This leads to the circular or helical motion depending on the angle between V and B. For a particle of mass m moving with velocity v in a magnetic field B perpendicular to V, we have that so r is mv over qb, where r is the radius of the circular path. We can write the full expressions for the Lorentz force as F is equals to Q parenthesis E plus V cross product B, where E is the electric field vector. We have some implications here. So when in the presence of both the electric and magnetic field, the particle's motion becomes more complex. The electric field can do work on the particle, changing its kinetic energy. while the magnetic field continues to change the direction. For some applications of the Lorentz force is the cyclotron or synchrotron. For cyclotron motion, we have circular orbits of charged particles under uniform magnetic fields can be used to accelerate particles by applying an alternating electric field. So particles gain energy and move to larger orbits. The electric field accelerates the particles and the magnetic field keeps them contained to a circular trajectory. So magnetism arises from the motion of electric charges. The Lorentz force is the key interaction between moving charges and magnetic fields, and it acts perpendicular to both the velocity and the field direction. In combined electric and magnetic fields, the interaction can be used for precise control, as in devices like velocity selectors. These concepts and properties studied are being used, for example, for plasma confinement in magnetic fusion reactors, where the behavior of charged particles in magnetic fields become crucial for energy generation. For example, for nuclear fusion, you need a high temperature plasma, which is just composed of electrical charges. Because of the high temperatures, the atoms are separate, so the atoms are not neutral anymore, and the electrons are extracted from the atoms. You have positive charges, you have negative charges, but the temperature is so high that there is no container that can contain that. So you need to have them like floating around in order to contain those electrical particles. You can use magnetic fields to contain them and keep them far from the walls so that the walls do not melt. You can accelerate them with electric fields, you can confine them with magnetic fields, and at some point you want to have them react and extract energy, just like what happens at the core of the stars. We will continue with more details of the magnetic field and their properties in coming lessons. May science be with you.